Hey guys, welcome back to my channel and this is Varun Tahin. In the earlier sessions, we have talked a lot about what matrices are and some of the operations it supports. Now, before moving on to the next topics on matrix, we need to understand some terminologies associated with them to understand the future topics better. So today we are going to learn about matrix determinants, what is its significance, and understand some more concepts like inverse, rank, column space and null space with regards to matrices. So let's start. Now let's understand what a determinant is. So by definition, a determinant in mathematics is a scalar value that is a function of the entities of a square matrix. Okay, and it allows characterizing some of the properties of the matrix and the linear map representation by the matrix. So the determinant of a matrix is denoted by det A or simply A by two vertical lines. Okay, where A is the matrix available for us. And you can note that it is the same symbol as the absolute value. And what is its significance? Actually, the determinant helps us to find the inverse of a matrix and tells us things about the matrix that are actually useful in terms of systems of linear equation, calculus and more. And it is only when this condition of matrix being a square matrix is true that we can calculate the determinant of the matrix. Otherwise, it wouldn't be possible. So we will see with the help of example how to calculate the determinant of a matrix. Now let's understand how calculation is done for a 2 into 2 matrix and a 3 into 3 matrix and derive its determinants. So first of all, as we have discussed earlier, in order to calculate the determinant, the matrix should be a square matrix. That is having the same number of rows as the columns, and then it is just arithmetic operation. So for a 2 into 2 matrix as shown on the screen and denoted by A, having elements A, B, C, D, the determinant of this will become AD minus BC. That is, the determinant of A equals A times D minus B times C. And it is quite easy to remember this when you think of it as a cross, where green is positive and blue is negative. So what we are doing here is we are multiplying the top left corner element with the bottom right corner element and then subtracting the product of bottom left corner with the top right corner. So this way this becomes a cross and we can do an arithmetic operation on any elements. So this is for a 2 into 2 matrix. Now a question arises that how will we derive a determinant of a 3 into 3 matrix? So guys, it is quite similar. It's just that instead of taking the element here, we will first derive the determinant of the 2 into 2 matrix in this and then do a arithmetic operation. Okay, so it will be something like this. So we will keep the three elements on the top as the base and multiply each of the element with the determinant of the square matrix inside it. Okay, so here EFHI is a 2 into 2 matrix for which we will derive a determinant and then multiply it by A. So it will be A into EI minus FH and then do a subtraction and then take B with these as the 2 into 2 matrix, that is DFGI. Take its determinant, multiply it by B plus take C and elements here which are DEGH. Take its determinant and multiply those. So this way you will get this equation wherein you can feed the individual value and get the determinant of a 3 into 3 matrix in this case. And the pattern continues for finding the determinants for a 4 into 4 matrix also, wherein we will alternate the signs and then find each of the matrix by fixing the first row, taking each of the elements in the first row and multiplying the determinant of the 3 into 3 matrix that is not present in that element's row or column. So by that way we will get the determinant of the 4 into 4 matrix. And likewise you can find out the determinant for n into n matrix too. Now you might be wondering where determinants are used exactly. So we have taken an example to showcase its usability. One of its usability can be to find out how much area is scaled. Okay, and this can be found out by calculating the determinant of the transformation. So you can see in this case the determinant is 6 and therefore it is scaled by the unit 6. Whereas in the second case we will get a determinant of -2. And can you tell me how can you scale the area by a negative number? So this can be done by flipping the orientation of the plane. That is, the determinant becomes negative suddenly in the 2D plane. So this was the case where we have taken 2 into 2 matrix, and likewise for the 3-dimensional matrix, that is 3 into 3 matrix, if we find the determinant, it can give us the volume of the three-dimensional object which is parallel piped, in this case taken as an example. Now there can be cases where the determinant of the matrix is 0, and when the determinant of a matrix is 0, the system of the equations associated with it is linearly dependent. That is, if the determinant of a matrix is 0, at least one row of such a matrix is a scalar multiple of another. So you can see in this case that the first row is a scalar multiple of the third row, that it is multiplied by 1 and it is exact, and therefore it is linearly dependent. So we have understood linear dependency in terms of vectors. So this represents that one vector is actually a scalar multiple of another. Okay. Also, there is another rule where if we take a dot product of two matrices and calculate its determinant, then it will be equal to the product of the determinant of the individual matrices. Okay, and we can calculate determinant with NumPy library np.linearalgebra.determinant by giving the matrix inside the method. Now we will see how inverse of a matrix can help us solve the system of linear equations. So guys, inverse can be really powerful in solving some mathematical construct which is hard to solve manually and can be automated via taking the inverse in Python. So let's say that we have these equations in hand with their coefficient and the values of each of the equation. Okay. So these three equations can be represented in terms of Ax equals to B, where A represents the coefficient matrix in this equation. So you can see that with each of the variable there is a coefficient associated, which is in this case 1, in this case plus 5, and in this case minus 1. So likewise for the other row, in this case it becomes 2, 3 and minus 2, and for the third equation it becomes minus 3 plus 4, and there can be another coefficient for x3 which is plus or minus 0 x3. So in this case it becomes 0, and therefore we have represented these coefficients with the matrix A. Then X can be another three-dimensional matrix represented by the variables x1, x2 and x3. So when we multiply A by X, we will actually have to take the dot product, which is multiplying each of the rows with this vector, and that will give us exactly this equation for each of the row, and their values are another three-dimensional vector and is represented by B. Now as we know that Ax equals to B, then X will become A inverse of B. And this can be easily calculated in Python by storing values in NumPy arrays for the coefficients or A, for the individual values of each of the equations in B, and then taking the inverse of A and doing the dot product with B to get X values. So this is how simple it is. Now let's understand what is rank, column space and null space. So first we will understand what is column space. Column space is nothing but a set of all possible outputs which represents the span of the columns of a matrix. And rank is actually the number of dimensions of that column space. Okay, so a rank 1 will denote a single line, rank 2 a single plane, and rank 3 a 3D space. So basically saying it is the representation of the dimension as we have seen earlier. But there are some exceptions to this, as in this case, where we have this matrix of 1, 2, 3, 6, but instead it has a rank of 1, because as you can see that it has two column vectors and those are collinear, that is on the same line, because one can be represented as a multiplication of the another, and so the matrix squishes 2D space onto a single line. So the column space of this matrix will be a straight line, and the null space is the space of all the vectors that land on 0 vector under the transformation, and it is called as kernel 2. And 0 vector is nothing but where the magnitude of the vector is 0. Now we have previously looked at what is the inverse of a matrix and how it is used, but we didn't speak about how it is calculated. So in this section we will see how actually the inverse of a matrix is calculated. So let's say that we have a matrix A, B, C, D, and we have to take the inverse of A. So the inverse of this will be 1 upon multiplication of AD minus multiplication of BC whole multiplied by the matrix by changing the position of A and D and putting negatives for B and C. Okay. So here the positions of A and D will be changed and the sign will be inverted for B and C. So now let's look at one of the examples. Here ABCD is represented by 0, -1, 1 and 0. And if we want to take its inverse, the A inverse will become 1 upon AD, which is 0, minus BC, which is -1, which is +1, multiplied by the matrix by changing A and D positions. So this remains constant because A and D both are 0, and changing the signs for B and C. So -1 will come in C's location. So ultimately we will get this matrix, and this can be imagined visually by first imagining the transformation represented by matrix A and then imagining the reverse transformation. So A represents an anti-clockwise rotation by 90 degrees. So A inverse should represent a clockwise 90-degree rotation. Now we have spoken about this earlier also, that when we multiply A by its inverse, we will get the identity matrix. And as we have spoken in this session, that A inverse represents 1 upon AD minus BC multiplied by the matrix by exchanging its position of A and D and putting negatives for B and C. We can clearly notice that AD minus BC represents the determinant of A, and therefore inverse of A can be represented in terms of its determinant factor also. And then there is a concept of identity transformation, which does nothing and do not alter the location of the basis vectors, which is I hat and j hat, which still stays at 1, 0 and 0, 1, like an identity matrix. Now we can verify to see if the system of equations have a unique solution, and we can do that by changing the vectors and looking at its determinant, whether the determinant has changed or not. So that will be all for today, guys. Hope you liked the content in this session. If you liked it, please encourage me by giving it a thumbs up. Also, please don't forget to subscribe my channel if you are new to it, and hit the bell icon if you don't want to miss any updates coming on this channel on data science. I will be seeing you all in the next session. Until then, thanks, take care and happy learning.